Alrighty, it's 5:03, so I think we'll go ahead and get started and people can continue logging in as we go. I just want to say thank you so much for joining us today for our workshop on the introduction to functional programming in R. My name is Nicole Swartwood, and I, along with my colleague Christian Testa, will be leading you through some of the basics of this topic in R. And so to get started, I just wanted to walk through a little bit of the structure of the talk. I'll be starting with a very brief discussion of functional programming in general. And then we will explore two families of function in R that facilitate functional programming, the apply family of functions, and then the map functions that can be found in the per package. For each of these, we'll start with some information via the slideshow, then transition to a live demo by Christian. So that's a lot to cover, so we'll jump in. Before discussing what functional programming is in itself, it's useful to sort of remind ourselves what programming is itself. Programming really can be thought of as like an abstraction of reality, whether we're thinking about environmental systems or financial exchanges or epidemic spread. It's at its core, it's just this abstract model of those entities on your computer. And there are different approaches to programming, known as programming paradigms, specifically object-oriented and functional programming. And we'll be focusing today on functional programming, which focuses on the evaluation of functions, as its name might suggest. And it operates through the use of variables and functions to sort of describe what is wanted from each line of code, which is sort of known as the declarative programming model. In contrast to that, there's object-oriented programming. I mention it here just to serve as a contrast to what we'll be discussing today. And don't worry if you don't know much about it, but if you are interested in learning more about the two, there's a tremendous amount of resources online. But object-oriented programming is based on this concept of objects, which contain within them the data and the code, and it really focuses on the how as opposed to the what of code execution. And just again, that's just a few really, really brief highlights about each of these paradigms, and there are far more nuanced and important aspects of these, but it really isn't necessary for you to reap the benefits of today's discussion. R itself incorporates aspects of both object-oriented and functional programming. In R, it's important to know that functions are first-class objects, which means you can essentially do anything with functions in R that you could do with data structures. You can assign them to variables, you can store them in lists, pass them as arguments to other functions, or create them inside functions, and even return them as a result of a function. And as such, we can leverage that to create more efficient workflows. And one of these ways to do that is is to use these methods we'll be talking about today as opposed to loops. And we've talked a lot about so far what functional programming is, but I haven't really discussed why it might be useful for you to implement in R. Using functional programming in R can be more concise and therefore easier to read and debug. And it can also be faster than non-functional approaches. But it is important to note that in the last several years, there's been a tremendous amount of work done on loops and they have improved in speed. So it's not as clear-cut as it used to be. But it's still a good practice to learn and leverage in your workflow. The first way that you might incorporate functional programming in R is through the use of the apply family of functions. which allow the user to apply a function to all the elements of a vector or a list or data frame. It allows the user to avoid the explicit use of loops, which can be lengthy and at times difficult to follow. And these functions are included in base R, so they don't require any additional installation typically. And before jumping into a few examples of the apply functions, it's important to note that at this point, the functions in the apply family are now considered legacy functionality. And so it's advised not to incorporate these into new code, but they are still very useful to understand for the maintenance of code bases, as well as just passing code on or updating it. Oops, sorry. Today, I'm just going to walk through 3 key functions of the apply family, each of which apply a function to every element of a data structure. The first of these is the apply function in general, which applies a user passed function to a specific dimension of an array. Most commonly, this is used to apply a function to the row or column of a matrix, but it can be expanded to multi-dimensional arrays, but I won't be discussing that today. The second of these is the lapply function, which is short for list apply. It works really similarly to the apply function, but instead it applies the user passed function to every element of a list and returns a list at the end of the function call. Finally, on this list, we have sapply, which is known as a short version for simplified lapply. It works exactly like lapply, applying a function to every element of a list. But instead of always returning a list, it then attempts to return the simplest possible form of the result. And to think about that, if we decide to run, like, for example, the mean of every entry of a list, and then we're left with a single value for each of those elements, it could be preferred to store that in a numeric vector as opposed to a list. And so that's what sapply is trying to do for you. I just wanted to briefly introduce you to the syntax of these 3 functions, and then Christian will show you some executed examples in the demo. For the apply function, you will typically pass 3 arguments, the first of which is the data structure to which you'd like to apply your function. And the second is called the margin, and this is going to control the dimension of the data structure that the function will be applied to. And the last argument is the function that you would like to apply to your data. Here on the slide, we see an example of how to use the apply function. We first define an example matrix here, which has 10 rows and 5 columns. And suppose we'd like to know the means of the data in each of those rows and each of those columns. We can use the apply function to determine this. In the first example here, we pass in our matrix as the data, and then we set the margin argument to 1, which indicates that we'd like the function to be applied across all the rows of the matrix. And then we pass in our function, which here is the mean function. This will return a list of length 10, which contains the mean for each of the row of our matrix. And in order to do this for across all the columns, it's the exact same line of code. We just only update that margin argument to 2, which indicates that we would like it to be the mean function to be applied across all of the columns of the matrix. And so that will return a vector of length 5 with the means of each of those columns. Now suppose that we'd like to apply a function across each element of a list. For example, what if we had a list of biometric data and we'd like to know the median of each of those values so we could better describe the underlying population? For this, we could use the lapply function to apply the median function to each element of the list containing this data. The general form of the lapply function requires you to pass in your data as a list and then the function you'd like to apply. And I've also shown here how you can use the pipe operator to execute this function. Here we also see an example usage of the lapply function to determine the median height and weight stored in this list that I've created here as an example. Each of this execution here will return a list of length 2, which contains the median of the height in the first element of the list, because that was the first element of the input list, as well as the median of the weight in the second element of the list. As I alluded to before, you might run that chunk of code in lapply and think it's not really necessary to store 2 numeric values in a list. This is a situation where sapply can become handy. It's used exactly like lapply was in the previous example, but instead of returning a list, it's going to return a vector of length 2, which contains the median of height in the first element and the median of weight in the second element. Using simpler data structures can often simplify future operations that you may need to do in your code. And it can also help reduce memory usage when writing programs that need high computational efficiency. So it can be nice to incorporate sapply when appropriate. I've discussed 3 of the primary apply functions, but before handing it off to Christian for the demo, I just wanted to briefly mention that there are several other apply functions in R. I'm not discussing those in detail, but I have listed a brief description of each of these here. And they really serve as an attempted answer to a more niche need or an attempt to solve some perceived shortcoming of the core apply functions. And if this is something that you'd like to learn about, some of these more nuanced or detailed functions, please let us know, because that's something we could put together in the future. And with that, I'll pass it over to Christian for a live demo of the apply functions.
Great, thank you. So first, I'm just going to put in the chat a link to a GitHub repository that I put together for today that has just one script file in it that I'm going to be walking through. And let me scroll up to the top. And so I want to go over some of the background stuff that Nicole talked about and then show some examples with apply. So just to reiterate some of the things she said, one of the things that's really particular about functional programming is that it means functions can be treated just like other variables. So that means that they can be passed as arguments to other functions. They could be combined in lists or vectors, and they could be used repeatedly in loops. And that's kind of special because it's not common to all programming languages. Some programming languages don't let you do those kinds of things. But R is nice in that way, and it does support functional programming. So first, I just want to go over some really extreme basics and make sure that everyone is on the same page about what functions are before we get to some examples. And I'll show you some of those examples of putting functions in lists and stuff like that, so you can see what I mean. These are some dependencies that we're going to use today. I'm just going to load those up. And I think it'll be obvious, hopefully, when I get to using each of those. But just to review really quickly what a function is, typically in R, you'll see that a function is assigned to a name. It's always declared using this function keyword. And then inside the parentheses go any arguments to the function. And then inside of that, is the body of the function. So that could be something like this. It could be something much longer. It could even be shorter. And typically in R, the return value of the function is whatever the last expression evaluated is, or we can explicitly use return and then put the return value in that call to return. So this is what your typical function will look like. If that's hard to grasp, if you're like really just beginning with functions in R, I'll give you an example of something that I use a function for pretty regularly. And since Nicole and I work in science, something we often are doing is reporting like estimates in academic papers and then reporting them with their 95% confidence intervals. But it always takes a really fiddly argument. We always end up wanting to have, in our paper, something like an estimate and then parentheses and 95% confidence interval, low to high or something like that. And so this is a really simple function we could write that would take our three numbers and it's going to do a couple of things. It's going to round them, it's going to concatenate them together, and then it's going to return the formatted string. So I'm using the stringer package here, the string concatenate function or strc from that function. And I'm using the number format function from scales to format my numbers with one digit past the decimal for each of the estimate and the confidence interval low and the confidence interval high. And I'm concatenating those together with the proper amounts of spaces, the opening parentheses here, a line that says 95% confidence interval to get this kind of a string. So this is a type of function that I actually use all the time. This is something that's actually very useful to me. This is not like a canned example. This is something I really do use. So this is an example of a function that, has practical value. So we could declare that function. By declare, I just mean like run that on the R console so that R knows about our function. And you'll see in my environment, now you see that shows up here as an object that we can work with under the functions section. And we can call our function with arguments. So you see when I call it, maybe I did some data analysis and I found that my estimate was 0.5 and the 95% confidence interval was 0.25 to 0.75. Of course, when we round everything down to just one digit of accuracy, you'll see that those numbers get rounded. So that's functions in a very quick brief and calling a function. So you probably are already used to several functions that are in R. Like functions you might be familiar with are things like mean or standard deviation or min and max. Those are some functions that get used quite often. Even other things like list, a lot of the data structure creator functions like list or C or data frame and things like that are functions. So you've probably been using functions a lot, no matter how you've been working with R. So one of the things that we were remarking on that's special about functional programming is that you can treat them just like other objects. So you can create a list of functions. So in this case, the object here called my functions, it's a list and every element is a different function. So you'll see that I have the mean function, the standard deviation function, the min function, and the max function. And then just like other elements of a list, I can use that double bracket notation that's particular to lists in R to call that. So this would be the mean of those values, the standard deviation, the min, and the max of those items. So I'm actually, referring to these functions and then calling them from inside this list that I've created. So that's what we mean when we say that you can put functions in a list. You can also pass functions as arguments to other functions. So this is a really canned example but just to illustrate the concept, here is a function. I've named it apply function to the iris dataset, and it takes a function that we'll call f as the argument. Or it takes one argument, f, and then it applies f to iris, and then it'll just return that output. But this is a very important functionality that's necessary to be able to do functional programming. So here in the next example, I'm applying the dim function for getting the dimensions, the number of rows and columns of a data structure. So if we do that, we see that the iris dataset has 150 rows and 5 columns. Or we could just pass ncall, the function for getting the number of columns, and that'll tell me 5. Or we could pass call names, the function for getting the names of the columns, and you'll see that that prints out the columns. And notice that I'm not using the parentheses on dem, in call, or call names. And that's because I'm not evaluating the functions here when I'm passing them as arguments. I'm passing the actual function itself, not an evaluation of the function. So that's a subtle point that's important about passing functions as arguments. And that'll be relevant for the apply family as well. So now that you've seen how you can do those kind of basic, simpler aspects of functional programming, let's meet the apply family functions, and let's start with apply. So apply lets us apply functions repeatedly over arrays or matrices. And as Nicole explained to us, it takes 3 arguments, the first being the data that we're going to use, typically a matrix or an array. The second being the margin, or in other words, 1 for rows or 2 for columns. With arrays, it's a bit more complicated since you can have more than 2 dimensions, but most of the time I find that I'm working with just matrices or 2D arrays. And so it really is as simple as 1 for rows or 2 for columns. And then the last argument, the third argument, is the function to apply. So what it'll do is it'll apply the function given to each of the rows or columns, depending on what's passed in the margin argument, that middle argument here. So for example, we might be looking at the empty cars data set, which if you haven't seen it before, it's just a built-in data set in R, and it has a bunch of numeric values in there describing different cars from a magazine from 1974. It's kind of a trivial little data set, but it's useful for us just working practically and pedagogically. So I might be interested in getting the mean across the different rows. And so for that, I would use the margin as 1. I would pass the mean function in the function name, and I pass my data as the first argument. And you'll see here, because the data have row names, I'm conveniently getting back a mean across each of these columns, or sorry, a mean for each of these rows, which corresponds to a particular car, and the corresponding mean value. This is probably not very useful in this example because, we're averaging lots of different types of measures. So that's probably not meaningful. A more meaningful type of thing might be to average across the columns. And so we could do that by just changing that 1 to a 2 here. And now we see the average miles per gallon, for example, for all of these different cars was 20, or the average number of cylinders was about 6.2, and so on and so forth. We could pass other functions like max instead of mean. So if I were to do that, I would see that the highest MPG car was 33.9, or the highest number of cylinders was 8, so on and so forth. So I think those are useful on their own, but I think something else that I want to show you is that you definitely can pass your own functions to the apply family. So something I might do is write a simple little function like count NAs, count the number of missing values, in other words. And the way I'm going to do that is I declare a function. It takes 1 argument. I determine a Boolean value for which values of X, the argument, are NA or not NA. And then I sum up the number of NAs, and that's how I'm counting NAs here. So I might declare that function, and then using the Palmer Penguins data set, which if you've never seen this before, it's a sample data set of some penguin observations from off of Antarctica. And they have different information that was collected on them, like their species and measurements about their bill length and flipper length and body mass, but some of them are missing. So if we actually look at the data, you'll see that for a few examples here, they weren't able to get the data that they wanted to, but they did take measurements on those penguins. So we might be interested in how many missing observations are there for each column. And so we could do that with apply penguins, 2 for columns, and then passing this function count NAs. And so what could we read off from this? We could read that there's 0 missingness in species and island. Okay, that makes some amount of sense. But then there's higher missingness in things like the sex of the penguins. And then it drops off quite substantially. And then we only have 2 missing observations each for their bill length, their bill depth, etc. Nicole mentioned that there are several other members of the apply family, like lapply, sapply, vapply, and mapply, but we really don't use these very much anymore now that the per package is around. So I'm not covering examples of them. And I wanted to underscore one of the things that Nicole mentioned, which is it is still really useful to know about these apply family functions because they do tend to come up in legacy code. Like when we get given code from someone else who maybe wrote their R code 10 years ago or something like that. The per package, I don't think was around back then. And, so you still might see these apply family functions in their code, but typically when you're writing new code, you'll want to use the per package for the reasons that we'll go over shortly.
Thank you so much, Christian, for those examples. I'd now like to transition to the second set of functions we'll be discussing today. As Christian mentioned, these functions are part of the per package in R. And the goal of that package really is to enhance the functional programming toolkit, specifically through providing complete and consistent set of tools for working with functions and vectors / lists. I'll go ahead and just apologize if I use vectors and lists interchangeably, since technically I think in the way that R is set up, lists are a type of vector, and I've tried to fix my code here so that or my wording here, but I am worried that I will make that mistake. So if you're confused, it's probably on my fault and not you. The core of the per package is really what I'll discuss today, and that's the family of map functions within that package. And they work sort of like apply functions in the sense that they serve to replace many instances of for loops in your code. And you might be asking, if we already had the apply functions, why did we need per in these map functions? If anyone has worked with the apply functions, you might know that they can be quite tricky to master with some of their quirks and differential expectations for each of the function calls, or just getting different types from different function calls, and those might not be what you anticipated. The map functions in per really seek to improve on these apply functions with a really specific focus on consistency. They will always return lists unless you specifically request something different. And they have very consistent input and output across the different functions in the family. Like you saw in the apply functions, they do still inherit the element names of the input data structure, which is really nice. And taken together, all of these really, of all these features, generally reduces the effort needed to read and write functional code in R. I also really quite liked, I was doing some research ahead of this, and I really quite liked this quote from R from Data Science. I'm not going to read through it in depth, but essentially it's just discussing about why per could be preferred to the use of for loops. It essentially allows you to break the common list manipulation challenges into smaller independent pieces, the first of which allows you to sort of reduce the dimensionality of your problem. That is, if you can solve the problem you're trying to implement in your code for one element of the list, per is going to work to generalize that solution to all the elements. So that's going to make your job easier. And second, through the different ways in the different functions in the per package, it allows you to make incremental progress towards a complex solution through the use of this smaller functions that can be strung together with pipes if you're using that coding technique. And so it can be a really powerful tool to enhance your coding workflow. Here are the three key functions from PER's map family that I'll be just walking through briefly today. The first of these is the map function, which applies a function to every element of a list or vector. The second is map2, and that 2 is a clue that this is actually going to require a pair of elements. So you need to pass in 2 lists or 2 vectors, and it's going to apply that function across every pair of elements from those past arguments. Finally, we have pmap, which you can think of as sort of a parallel map. And this is going to apply a function to a group of elements within a list or a vector. You'll see later as I describe it, it's really trying to serve as a generalized version of map2. So we can, instead of having to continually pass in n lists to our argument, you can pass in a list of those lists and then apply your function across all of those. And just like with the apply family, there are more complex functions in the map family, which we're not covering today. But again, if this is something that you'd like to dig into more in the future, let us know. First, I wanted to just discuss the general map function. This function requires 2 arguments, the vector or list to which you want your function applied, which is represented in this figure by the column of orange boxes. And each one of these boxes is representing an element in the vector or list. And then you also are going to pass in the function that you'd like applied. It's the map function, when you call it, is then going to apply the past function to each element of the list that you have supplied. And then it will return a list with each element of that list representing the result of each one of these individual function calls. Here is the syntax of this in R. Like the apply functions, the map functions can be used with or without pipes, as seen here. In this example, I am looking to find the mean of each of a couple of samples of data. And it's what can be useful here with the map function, as well as when applying it, you don't necessarily have to have the same number of elements, or each element of your list doesn't necessarily have to have the same dimensions. So you can see here, the first element of my list, my first sample, has 10 dimensions or 10 elements, whereas the second one has 30. But we can still apply the map function and determine the mean of each of those samples. So here it is without pipes, and below you see how you would pass it through with a pipe. And this code here, when executed, would return a list of length 2 with the mean of each element of the input list contained in that output. The map function itself has several different forms that allows the user to specify the type of the list that is returned from the function call. In addition to the general map function, we have functions that force the return of a logical, an integer, a double, or a character, vector, or list, each of which is indicated by a suffix in the function name. And if the type, when you execute these functions, if the type of the output cannot be coerced to the required type from the function call, it's actually going to produce an error which will break the code from executing, which is really nice because it kind of helps eliminate silent bugs in code development. If, for example, you're trying to coerce your output to an integer list and you didn't realize that your input list actually had like the names of individuals in it, and then you were trying to find the mean of that, this would throw an error and not allow you to execute the code. So you wouldn't just have a silent NA in your output. Here is a depiction of how the map2 function works. We see that it looks quite similar to the map function, but instead of just the orange representation of the list, we actually have two different lists or vectors passed into the function, one orange and one blue. When executed, the map2 function will apply the desired function to the first element of the orange and the blue vectors, as we see here on the right-hand side. And then it'll do the same for the second elements and the third and the fourth and so on. It then will return a list with each element representing the result of each of these function calls, just like we saw in the map function. Here is the syntax for the map2 function. In this example, I'm looking at determining the minimum value of each element location in two vectors. And so thinking through why this might be practical, if you were trying to, if you were collecting temperature data at two different time points, you might store each of those time points in their own specific vector, with each element representing a specific entity, such as like a monitoring location. If then you wanted to know what the overall minimum temperature is for each location, regardless of time, you could use the map2 function to pass in each of these vectors as well as the min function, and it would return a vector of length 12 with the minimum of each of the element pairs within it. Finally, I just wanted to briefly mention the PMAP function. As I mentioned previously, the primary difference between PMAP and the previous two functions is that you specify a single list that contains all the vectors or lists that you want to supply to your function. And it's really can be seen as a generalization of the map2 function to allow for additional data structures to be included in the application of the past function. And so here we have the boxes representing a list, and each of the different colors represents either a vector or list that you want the past function applied to. And we see here how this on the right-hand side looks extremely similar to what we saw with map2, but instead of 2 arguments being passed to the function, we have 3 because that was the length of our list. Again, we will return a list with each element representing the result of each of these function calls. Here is the syntax for the PMAP function. We see that the actual syntax is exactly the same as we saw with the map function, but here the data structure will contain more data than what we would pass in the map function. For example, what I have here is a list of 3 samples that we want to calculate the sum of. And so we just pass in that along with the sum function, and it's going to return a list of length 10 with the sum of each of the first elements in the first element of the list. So that would be if you had like the first element of sample 1 plus the first element of sample 2 plus the first element of sample 3, that would be what served as the first element of the output list. I know that probably feels like a tremendous amount of information to absorb, but I am going to pass it back to Christian for a demo of the map functions, and I hope that helps sort of solidify in some of these concepts.
Great, thank you so much, Nicole. So I'll be mostly talking about just the per map function, because in my view, if you're starting out from just learning functional programming, I would really want you to master just the per map function, and then the other functions that Nicole was talking about will come much easier once you have a really good grasp on that. So let's get started with the map function. So just to make things really simple, map is a more modern replacement for apply and for sapply and lapply. It does return a list by default if you just use the per map function. So you'll see here that my data are structured in a list as indicated by this double bracket notation here. This is saying the first entry was 1, and then 4, and then 9. And this is to be expected because I passed this function that squares its arguments to map, and I gave it this argument 1 through 10 for the data. So that's just a really simple example using map, but we could talk about now, before we get into a few more examples, what are some advantages compared to the apply family? So one of the things that the map function does is that it always returns a list. Same as lapply, but as opposed to sapply, which simplifies your data, you won't get unexpected output from map because it won't make automatic decisions that might be counterintuitive to you. It's also tidyverse compatible in the sense that it supports piping from other steps prior to it. So whereas the apply family functions, let's see, well, this is actually similar to the apply family functions in that they take your data first, but it is one of the perks of the map function. So here's an example that I might use in real life. I might have some complicated data storage structure. I might have directories with files inside them. My files might be inside this directory. And these might be the files, the CSV files that I want to load. So I could do something like I could declare, my directory. I could declare my files for reading. I could use that string concatenate function from before to concatenate my directory with the files for reading and then pass that into map. So again, it's pipe compatible. And you'll see what happened here is that after I passed these files into map and then gave it the reader read CSV function to call, it returned to me a list with 3 tibbles in it. So the first tibble is the data loaded from uscities.csv. The second tibble is the tibble loaded from usstates.csv. And the third is earthquakes.csv. And I'm doing something subtle, and I think a really nice feature of map is that if you need to pass this function additional arguments, you can actually just pass them after you give the function to map. So this is an argument that goes to reader read CSV, and I'll actually show you what happens if I run it without that, so you can see what I am getting as the advantage here. If you look at when I call that, you see it spits out a bunch of just helpful diagnostic messages about how it's reading in the data. And I didn't really need to see that printed out on the console, but since I already knew that it was reading the data structure the way I wanted it to. So I just, it actually recommends, set show call types equals false to quiet this message. So that's what I did right there in that step. So this is just how you pass an additional argument to the function that you're passing to map. Okay. Another benefit of the map function or the per family in general is that you can use this tilde syntax for defining functions. And it's a bit abbreviated and shorter than the way we usually write functions out in R. So sometimes it's called the formula syntax because this tilde is used for formulas in other contexts in R, particularly in modeling contexts. And basically the way that you should read this is that the tilde indicates that the body of the function follows and dot represents the single argument to the function. So this is a really trivial example. Like I'm just using this to show you how this works. So here I'm mapping onto the penguins data set, the summary function, and I'm just calling a function that calls summary on its argument. This is exactly the same as calling map penguins summary. So this, because I'm declaring here a function that takes one argument and passing that to another function, it's exactly the same. But you'll see what we're getting is we're getting the results of summary called on each of the columns. This is just to show you how this tilde dot syntax works with like the easiest possible example. But then what's a more complicated example? Here's something that I'll use occasionally is I might want the 95% quantile range of numeric variables. So like I was saying before, you can use the pipe operations with per. So we're going to pipe the penguins data set through this select function from dplyr. We're going to select only the numeric variables. So that's just to remove, there were a few variables in the penguins data set, like their species and the island that they were from that were character or factor variables. We don't want those since I can't compute 95 quantile intervals on those. And then I'm going to pass this numeric data, just this tibble of numeric columns to map. And then I'm going to use this tilde notation. I'm going to call quantile on my data. And then I'm going to ask for the 2.5 and 97.5 quantile. That's 95% of the data lies in that range. And I'm going to pass it also na.rm equals true to say like, just ignore the missing data, because otherwise it will return missing for those quantiles. So you can see here, these are 95 percentile or 95 quantile ranges for the data. So we could say that between roughly 3,000 and 5,800 grams is the range in which 95% of the penguin's body mass lied. Just in the observations. So this is another example using the tilde and dot notation, the formula style of declaring functions in line in map. So this is a little bit abbreviated compared to spelling out the whole like function and then giving it an argument name and then using the brackets. It's just a shorthand. You don't have to use it. A lot of people do. Another benefit of using map is that it has a really handy syntax for extracting elements from nested lists. In general, I think that the per family, the per package, its greatest payoff is how well it supports working with lists, complicated list structures, and things like that. So in that sense, this is one of the most useful features. And whereas the apply family doesn't have any kind of shorthand or easy way to do this besides declaring a function that extracts a certain element, the map function does. So we could have some kind of data structure. For example, here I have some of the characters from the Harry Potter movie series and book series. And I have different elements in them. So like name, their gender, their pet, and things like that. And if I just declare that object, now instead of passing a function to the second argument of map, I'm passing a number 2. And that's actually just saying I want the second element from each of these list items, each of the items in this list. So if I do that, you'll see I get the gender in each case, since that's the second item. I also could be more specific and use a character value here, a string value here, and give it the name of an item in the list. And so here I've used name, and you'll see that that's getting each of the items. And I could also do that with another of the values. So I could get pet, and you'll see here that this is being kind of friendly to me in the sense that since I get a list back, I have no problem getting single values back for the first 2 characters. But then, you know, Ron Weasley had 2 pets, so he has a nested list here. You'll see that for him, we have 2 elements in that list. So no problem dealing with nested complicated lists with map and per. And there are these handy features to be able to extract elements. And then I think Nicole highlighted this, that there are type-specific variations of map, like map double, map character, map logical, etc. And that's in contrast to vapply from the apply family. Vapply, I think, had a really, really tricky syntax to use, even for me. I would always find that I was trying to wrestle with it. It was always a struggle, whereas I find that per map just works. So for example, we might use functions from above like map double always returns a double. In other words, a double precision numeric value. So just numbers in essence. So we could use map double, and you'll see now these look a lot more like vectors like we're used to, and they're numeric vectors. We can even do type of on the output and see that indeed it's returned a double to us. Or we could use map int, and those would be integers. If we check the type of that output, you'll see it's integer. We could cast the values to characters and use map CHR for character, and you'll see that, okay, those are characters. It does look like, while I was preparing for this talk, that they're going to deprecate automatic coercion of values in per, which I think is a good thing, because the whole point of these type explicit functions is that you automatically can infer from the data either the program either succeeding or returning an error that your data were processed correctly. So you'll see here, I returned numeric data in the function that I called, and then it did automatically coerce my data, but it's letting me know the automatic coercion from double to character was deprecated in per 1.0.0. Please use an explicit call, and all of this is returned as a warning message. So this is presumably letting me know that this functionality is going away at some point. So just to let you know. We could also use the per LGL, for short for logical. So here's an example of a function to test for if a number is even. So I could have x divided by 2 is remainder 0 is my test for whether or not a number is even. And then I could call that on my vector of numbers. So some different reasons we might want to use these type-specific versions of map. We get a guaranteed output type. So sapply might, sometimes it will reduce our data type to a vector, sometimes it won't, and it's kind of just guessing when we want to do that. So we might not be comfortable with that guessing. We would rather just be explicit about what we want. And then, if we don't have strong guarantees on what our input data type is, then having more explicit guarantees on our output data will make our program more reliable. So for example, in like user-facing web applications or something like that, again, we might not be comfortable with that kind of guessing. If the users are putting in different kinds of data, we might want to be more certain of what to expect from our program. And finally, I think it's worth noting that there's a certain upside in terms of readability, that when you read the code, whenever there's a line that says map double or map LGL or something like that, you automatically can know from just reading the code what to expect. Whereas with sapply or with lapply or anything like that, you might not know exactly what to expect from the output of that step. I did want to talk about a couple more advanced applications of per map. So a few of the examples that I'm really fond of are around building lots of models very quickly. And the one that I'll talk about after that is around building lots of plots really quickly. So I find both of these are really helpful in kind of data science adjacent practices. So one type of modeling workflow that I might use, and I do use occasionally and frequently, is stratified models, where I build different models for different subsets of the data. And so I'll use this function nestby from dplyr to build essentially nested data. And let me just show you what that looks like first. So I say I pass my penguins data to nestby, and I nest it by species. And you'll see in this tibble, now I have data in this data column that are those are each themselves data frames. I think they're tibbles. And I'm going to pass that then to mutate from dplyr. And I'm going to construct a linear model in a column I call model. And so if I do that, we can look at this, and you'll see that now I have these LM, linear model object, in a column called model. And now, just since this is like a column, or it's actually a list column, I can use that with map. So I might call on that list column, the model column, I might call broom tidy, which is one of my favorite functions for extracting features from a linear model or any type of model that it supports. So you'll see here, now I called map on those models and I called broom tidy on each of those models. And you'll see I'm getting out the output of the coefficients, their standard errors and their p-values. Actually, one of the useful things to do here would be also to specify the confidence intervals. So now I'm getting confidence intervals for low and high, the 95% confidence intervals on each of these effects. I could do other things, any other functions that take models. So I could get the AIC of the models. So you could see that the second one is getting slightly better fit. But you can read more about fitting many models in the R for Data Science book on in the chapter on many models. The other example I wanted to show was how you might create a lot of different plots using per and map. So for example, just still using that Palmer Penguins data set, there might be a handful of different columns. Like I might be interested in this numeric type column, except for year. Year was also numeric type, but this plot format won't work as well for them. And I might have some complicated plot structure that I want to apply to the data repeatedly. So I might want to have like a histogram with a density plot laid over it and a title. And so in this case, I'm just going to define a vector of the column names that I want. And then I'll pass that to map, and I'll use the AES string function inside ggplot to pull out that value from the data frame. I'm passing data as penguins explicitly. And again, note that I'm using that tilde notation with the dot here just to use shorthand a little bit. And then I'm passing that again in the title. So if we do that, it will render each of these as plots that we can look through. So I could quickly now like see that they've shown up in my R studio session, and I could look through each of them to see the distribution of the data. And we could do, we could make much more complicated plots than these, but what's really handy is I didn't have to repeat myself. I didn't have to call the same ggplot code multiple times on each of these different functions. And I could have assigned that output to be a list of ggplots as a variable, and I could have saved that somewhere or kept looking through it. But I think this is really handy when you have a lot of variables that you want to quickly look through. It can be really handy to automate writing some, histograms or box plots or density plots to take a look through what your data distributions are. So that's it for my live demo. I hope that's been really helpful to you. And I think if there are some questions, I think Nicole and I have some time to answer them.
Sure, I can toss one out there. So I actually have a very specific one. I know you can put in lists, but are you able to input and have it process data frames? I guess I tried making a list of data frames using lapply, but that didn't work for me. So is that something that you could handle with maps?
Yeah, definitely. So typically what will happen with map is you'll get back a list of data frames, just like you were describing. And I totally can understand how you might have had trouble with lapply or the apply functions. I'm not quite sure immediately off the top of my head what the problem would have been, but it's somehow not surprising to me that you did run into a problem. Nicole, do you have anything? Yeah.
No, go ahead, Robert. Sorry.
Oh, I think the problem was almost certainly user error.
Okay.
But yeah,
well,
it was just...
I mean, there's something to be said for user error tending to crop up more with the apply family functions because their documentation is really technical and hard to parse. And so I think you should give the per map functions a shot and see, what you get.
Yeah, I'll take a stab and let you know how it goes.
Sure.
I know there was a request for resources in the chat, and I just wanted to say that if you weren't following the chat, that the end of the slideshow does have some additional resources and the URLs to go to those, and we'll be posting those, I believe, on our GitHub. So that's something else to check out if you want to learn more about functional programming in R.
Regarding the 3D array question, I think that tends to be more about if your data are better structured as a 3D array. Like that tends to be more of a question about what is the right structure for your data than, what's the right way to apply functions to it. I will say that there are some times where I've been preferring to use like nested data frames recently, like that are supported by Tibble and that nest by function that I was showing from dplyr, where I might have used to have used a higher than 2-dimensional array. And those settings are specifically when like some of the dimensions are like categorical, right? And so if like we have different data for data frames for, like different categories, categorical subsets of our data, then I might use nested data frames. But in general, if you have truly like multi-dimensional data, then it can make sense to use a 3D array. I find that typically I do spend time thinking about like, does this really have to be a multi-dimensional array? Because it gets harder to program with. I tend to find that it does. I mean, Nicole, what do you think?
The code I work with very often uses 3-dimensional arrays, and I think I quite like them. So I'm on the opposite end here. I think it's nice to show, especially if you have like consistent structure anticipations for 2 of those dimensions, that, it's really just varying based on whether it's like an iteration of a simulation or a model, but everything within the other 2 are different. So I also, in contrast, find them easier to program with as opposed to extracting elements from a list. So I do think it kind of is personal preference a little bit as well. I think it depends on if you prefer to do a tidyverse version of coding or more of a base R version of coding. And I think that even though we like to think that there's not 2 camps, I think there is, unfortunately.
Oh, yeah. So that question about the ... density ... where does that come from? That's a computed variable that ggplot provides for the histograms example. And the reason I used that is because the histogram plot typically is on a scale of counts, whereas the density plot is scaled so that the area under the density curve has area 1. And so they're on vastly different scales most of the time. And so we have to rescale one or the other. And it's much easier to rescale the histogram plot to be on the same scale as the density plot. And ggplot automatically provides some functionality to be able to do that. And that's what that ... density ... argument in the Y value was for. And it's something just automatically provided.
So what are the dots doing? Are those what you need to call the density function? Or
no, the dots on either side are really just a special syntax to let you know, like, hey, this is something from ggplot2, and it's a computed statistic. It's a computed variable, not like a usual, not a column from your data or something like that. It's basically just giving that variable, like a quite different looking name, so that you don't accidentally confuse it with columns of your data. And so it's more readable.
So could you do like ... smooth ... to call a smooth plot?
No, there's only certain ones that are provided by ggplot2. Let me see if I can find some documentation on that. I'll have to get back to you, Robert, because it's a little tricky to Google for ... density ... since most search engines will ignore the dots. Oh, so actually, I'm going to say that this is a good starting place, because this is someone with the same question as you. They were posting on the RStudio community pages. Basically, like, they've seen ... density. Another one is ... count, ... panel for when you're using faceted panels, and asking, like, where is the documentation for this? And the accepted answer has two links, one on calculated aesthetics and one from the ggplot2 documentation pages. But one of the things that's importantly highlighted in the answer is that there's a new syntax in one of the recent versions of ggplot2 that uses a function called stat. And that allows you to do what you were describing, Robert, where you could pass like stat and then some function of your data that you may want to use to transform it.
Thanks.
Yeah. All right, should we wrap up and take off? Thank you, everyone, for coming. It's been such a joy.
This was quite useful. Have a great day. Bye.
Thanks, you too. Bye.